presentation so far, they were excellent. So my head is full of LMBAs and whatever else now, so I hope I can remember what to tell you about matching. Okay, so my subject is broadband matching. So where do you get the matching networks from? So let's dig into that. Let me just get this thing to move. There we are. Okay, so main challenges of matching is usually you have complex source and complex load, so that makes things difficult. And you have to, a big part of the problem is to find targets. What should you match to? This is complicated, as you've seen, by wide bandwidths, very often also by very low impedance levels. And in matching, we're not concerned only with fundamental frequency matching, we also have to deal with harmonics. So suppression as well as control to get whatever mode of operation we're interested in. Things are also complicated by discontinuity effects. So we need EM simulators to take care of all the discontinuities in the design. And things can generally be screwed up by output capacitance. And as you heard from previous speakers, also the input capacitance. But in a sense, that modulation is captured also in the output circuit by changing the harmonic content. We'll talk about that later. So my talk will go first about how do we get appropriate targets, especially in this design environment, which is the amplifier design with it. And then once we have the targets, how can we solve these things? So that is basically how it is structured. So setting up targets, we all know load pool and source pool. So you buy your fancy equipment and you spend lots of hours in the lab and you get targets from load pool and source pool. The better way is to do things via the intrinsic transistor. So how to do and how is this done in the ADW? Now we've seen the intrinsic model of the transistor before. So what's different here is you can assume the load for this intrinsic device is a cascade, and then you can hope to embed it as the inverse cascade. But in generality, you need something more. So what's happening here is you have a mapping. So you map the intrinsic output voltage, the intrinsic driving voltage to the external voltages. And you can do it with a mapping like this. So basically, the voltages is mapped by mapping coefficients to the intrinsic quantities. And from the intrinsic voltages, you can get the intrinsic current. So this assumes linearity, but we will see it's not a big problem. It usually works pretty well. So in the ADW, you map the intrinsic device to the external device. And this mapping also allows feedback. So there's no problem if you apply feedback to this, it will still be valid. So even if you have loss, it will still be valid. So the mapping is actually pretty general. The only limitation is it assumes linearity. Now, this is a comparison of typical intrinsic load line. So intrinsic load terminations. So this was done for a 10-watt GAN. So the intrinsic load line over frequency, 1.4 to 7.35 gig, would follow this green curve in the ADW. Now, the good news is if you look in my office with harmonic balance, that this is harmonic balance, you can see they are pretty much the same thing. It's a very small difference between them. And this is not an exception. This is the rule. So as a rule, if you follow this approach of doing that mapping, you will get fairly close correlation between the intrinsic load lines as you see them in the ADW and as you see them in the harmonic balance simulator. Now, to calculate power, so first step is to do the mapping. So you actually know if you have a certain external load, what does it look like intrinsically? The next step is the Cripps approach. But this is now a generalized Cripps approach. So if you know the intrinsic load line and you have a voltage waveform, you can calculate a current, and then you can calculate the load line. So this is the dynamic load line. So this is the class B. So in the ADW, you can set 5 boundary lines. Now, I made this current boundary line go downwards because I like the idea of limiting the power. but as a rule, it would be flattish, or could have an upward slope. But you get this from the IV curves. So preferably the pulsed IV curves, but if you don't have them, you can use the static IV curves. And you make these boundary lines basically follow those IV curve boundaries. So that defines a knee for you, and the knee could be sloped. So usually it would turn around here somewhere, and then the maximum current boundary, you have a breakdown boundary somewhere, and minimum current boundary for class A or whatever. Now the good news is this applies to all the classes. So this environment can do class A, B, C, not C, all linear classes, B, F, inverse F, and also a thing I call B2, but we can talk about a little bit later about B2 if we have time. So this is the class B load line. Now, interesting, we have heard about continuous modes. You can see these things are wrapped in tightly, so they're resistive. But this one is open. So this is a continuous class operation. Now look at the voltages. The current this is class B. The current is more or less the same, the peak current, but the voltage has increased quite a lot. So this voltage stopped here, but that one stops quite a bit further. So that is a question again, can your device handle the bigger voltage? If it can, good. If not, then continuous mode is not for you. Now the interesting part is, while these load lines look very different, the power and the efficiency are actually the same. So that is the whole point of continuous mode operation. So this is for class B. This is showing it for class F. Oh no, sorry, this one is actually inverse class F. Where's my class F? This one is class F. Let's start with class F first. Now what I like about class F, see how nice it hugs this knee. And even with the continuous mode, it's really sitting on that knee all the time. So that's actually a very nice feature of class F. If you look at class B, it is sort of tangentially. And if you look at inverse class F, it's also fairly good. Now, interesting point of inverse F, you pay a price in a continuous mode for the B and the F, you need more voltage. For the inverse F, you need more current. So then the knee will mess you around a little bit. So you see here current's at 1.575 or whatever, and there the current will go to 2 amp or whatever. So you pay a price for inverse, for continuous mode operation, and the inverse class F you pay more current, and the other two you pay with more voltage. And effectively this will mess also will mess with your efficiency, because if you go there, the minimum voltage will be higher than in that case. So it's not always, it depends on where you chose the current. Now, important to understand, you don't have to make the current the maximum. You can drop the current to any, with these boundary lines, you can drop the current to anywhere you want. You don't have to follow what the device can do. You can follow what you as designer want to do. So these are showing dynamic load lines for the different classes. And with those dynamic load lines and the model, and the intrinsic impedance, you can basically calculate the power and efficiency. So point is, this is not harmonic balance, but sort of generalized Cripps. And using that, you know the efficiency, you know the power, and the assumption here is hard clipping. So when you hit those boundaries, the assumption is that is the power, and I call that the maximum unclipped power. Now, what happens beyond that? Now, you can't model it linearly, but there was a person, Johnson, I have it in references at the back, long ago wrote a paper on this saturation curve for transistors, and I use that in developing oscillators. It's a beautiful curve. It works very well. So beyond maximum unclipped, you go for this compression curve. And then effectively, you can also model compression and the power beyond that fairly accurately. Obviously not exact, but you can follow with a few fitting constants what harmonic balance is doing fairly closely. So the good news is, if you follow this approach, with a linear program, you can calculate power and efficiency too. Now, again, knowing the intrinsics, you can find contours. So basically, like Cripps did, this is now just with 4 boundary lines, so 5 boundary lines, so not only a maximum for the voltage and current, more general. So this would be over frequency. The green is low frequency, and as you go up in frequency, it goes to the magenta. Now these lines are very interesting. They are maximum efficiency lines. Now what does it mean? If you look intrinsically, at that point, the intrinsic resistance is a pure resistor. And that makes sense that it should be at maximum efficiency then. So as you move off that, it becomes reactive, and it becomes reactive, and basically efficiency will drop. So with a power contour and the maximum efficiency line, you already have a lot of information. So ADW can generate these things. Now, to create a matching problem, it doesn't help to tell a matching solver, here's this contour. He doesn't understand this contour. But what it does understand is it understands circles. So what happens in the ADW, it can automatically fit circles to, if you decide you want this power, it can center a circle in the middle of a contour, or you can center it around the peak power point. Or you can do one step further. That is a maximum efficiency line. You can say, now, if the Q is, say, 1, instead plus 1 or minus 1 for the reactance. So if it was 0 resistance, you would be on that line. If there was some reactance in here, and you measure it in terms of Q. So if the Q is minus 1, it would be on that line. And if the Q is plus 1, it's on that line. Now, also in continuous modes, you cannot have just arbitrary reactance added to the resistance originally for the original mode. You limit it. You can only add so much reactance. So this is the same concept. You can add so much reactance to say I have so much Q. So basically, you accept this Q and you accept this Q, and then this area, all of inside this area will be good for efficiency and power. So this is what this is telling you. So if I then choose which circle I want, I can basically target a circular area which will have reasonable power and efficiency. So that's the basic idea. Again, from knowing the intrinsic load, you can use all the continuous mode theory. So you can say, I have a continuous class B. I know where the intrinsic fundamental should be. I know where the second harmonic should be. I know where the third harmonic should be. But what is it externally? Where the matching network will be, how does it map? And this tells you how it maps. So the fundamental will sit there. The second harmonic will sit there. And the third harmonic will sit here. Now, these are interesting. The red is low frequency and the green is high frequency. So these go clockwise. Now that was done by cheating a bit. Oh, I'm not cheating. Yeah, it takes long to explain, but basically, normally these will go anti-clockwise. But you can make them go clockwise, but I'm not going to talk about it at the moment. This is the third harmonic. So you can see you will have to go around the Smith chart for the second harmonic, and then quite around again to get here again to get a third. So this will not be quite so easy, but you can do it. So for narrowband, it's easy. But as a rule, what you would like second harmonic, and then just a little bit further, you would like third harmonic. So it goes in a continuous flow. But that's not always going to work. It depends on the transistor, it depends on the frequency, depends on many things. So this is an example then of getting a target from continuous class mode theory. This is more interesting. We all know about second harmonic clipping contours, also great work by Cripps and company. So this is now representing that. So that's the intrinsic load, fundamental load line chosen. This is the second harmonic contour, so basically on the dots there and around the edge of Smith chart. But typically these contours go outside the Smith chart, but that's negative resistance. So I just clip them on the edge. So basically at this red frequency, you can have all the area there for the second harmonic. And then at the green one, which is the highest frequency, you can only have the area here for that harmonic. So you can see you have fairly large areas in which you can have the second harmonic, and you will still have good performance. Now interesting point. What do you mean by good performance? The power will be the same, but the efficiency will not, because if you pick this as a second harmonic, it's lossy. And on that lossy line, there will be losses in the second harmonic termination. So basically, the efficiency is not constant, while the power is constant. So you have to have lossless, not to have power in the second harmonic. So basically then you can also do clipping contours. You can do continuous any class, so F, inverse F, whatever. Another way of setting a target is just pure brutal optimization and tuning. Now this circuit is basically a triplexer. So this part is doing the load, fundamental load. This is doing the second harmonic. This is doing a third harmonic. And you the software is set up to just optimize things. It understands whatever to do. So this, you can just optimize and find what is the optimum. If I want class F performance, what should those things be? And this is an example. So it would get you want this for the fundamental, you want this for second harmonic, you want that for third harmonic, and the intrinsic load line, dynamic load line would look like that. Now, interesting, again, we are not usually only interested in power and efficiency. There are many more things that are important. So this is maximum unclipped power. So you can see sort of 41 dB. So that's where it hits the clipping lines. Then it can come by compression. You can go further. So this, in that case, can do 2.5 dB more. So that's the compressed power. This is the gain compression. Interesting, the gain compression as calculated by a curve usually agrees fairly well with harmonic balance too. This is the gain you would have for the stage, large signal gain. This is the small signal gain. And this is group delay. These are stability factors. Now, these are usually over the pass band. So this is the pass band. This is the gain variation. This is the VSWR variation, etc. But this is over the whole frequency range, stability. So that's normal relate stability factor. This is like mu prime and mu. This is short stability factor, load stability factor. So it's conditional stability. This is conditional stability. That is absolute stability. So basically, when you find the optimum load line, you would want to look at all these things, and it will change for different load lines. And you can optimize to have whatever target you set to get it. Now, from a matching viewpoint, in the ADW, you match the fundamental to circles. So you can say, okay, at the low frequency, I can be in this circle. Then I can be in this circle for next frequency. And at the highest frequency, I can be inside that circle. And then for the harmonics, these I call harmonic sectors. So basically, there's a local origin, and then it hits the Smith chart edge at 2 points. So all of these things are defined by 3 things. Some center, and then 2 edge points. And also then the sequence in which you define the first point and the last point. So if I say the first point is this one, and the second is that one, then I have a small area. If I say this is the first point, and the other one's the last point, then the area would be around this way. So it goes clockwise. So then it would be the big area. So you see, you can find most areas by using these sectors. So the sectors works well for harmonics. Whether you find the targets by local or by ADW, it doesn't matter. So whatever target, you can set up circles for the fundamentals, and you can set up sectors for the harmonics. This just explains circles more. So I can target the circumference of a circle. So sometimes I want a specific this and that. So would go on a circumference. But usually the inside of a circle is okay. And if I want rejection, I say the outside of the circle is okay. So this basically says constant gain. The gain is, say, minus half a dB on the circle. So outside would be more dBs loss, inside would be less dBs loss. So effectively, you can create many effects by choosing, is it inside, outside, or on the circle. So this is what the software wants for matching. So you need to find circles and you need to find sectors. Now, how do you solve, once we have the problem defined, how do you solve it? Well, many of us know Smith chart techniques, so that's fine for single frequency. Doesn't work so well for wideband things. We can optimize, we all know that one too. So we start with some reasonable solution which we pulled from somewhere and we optimize it. We can use filter theory. Now filter theory is great, but it is meant for filters. So its main emphasis is on pass band, so allowing signals through, and then rejection, so killing signals. And it's doing both very well. Now, in the matching network, that's not necessarily what you want. You want the pass band through, And then you want harmonic performance control, which ideally would like also to kill it. But the point is you also want impedance control. So the focus in a matching network is more on impedance control than is just on gain control. So effectively filters can be used, but it's not really the way to go. Now for real matching networks, good techniques were developed. They're called real frequency techniques. That was done by Carlin, Yalman, and people like that. And so I've done the references for those who don't know. So I'll explain a bit about them. And then in ADW, I use an approach called transformation queue approach. We'll see how that works. So basically, those are your options to solve things as a rule. Now, just an example of ADW, show a bit what it looks like. You can, if you use filter theory, you can, as a wizard there, this thing will design a transformer, and you can have geometrical mean design, maximum fat, or Chebyshev, and you can say how much your resistance must change, and it will give you a filter that will do it. The point then is, if you look at the performance, this is a Smith chart, but it's normalized for the input on to 25 ohms and for the load to 100 ohms, because those were determinations. So you can see the match would be there in this middle, but it actually makes a little curve circle. So it's doing the pass band not so wonderfully good, but it's also will do something similar, some other big circle in the rejection band. So it's doing two things: it's controlling the pass band and it's controlling the rejection band. So its purpose is slightly different than what we want. We actually would like those to be dots, which they are not. So in the real frequency approach, there are different real frequency techniques, but this is now more some fancy algorithm. A good one was this original one by Carlin. Now what happens here, you have some complex source you want to match. So you look at the conjugate of that, and then you approximate the resistance with such line segments. So the point is, if you have a matching network that has minimum, if you have a minimum impedance matching network, it means the last element is shunt. So then it's minimum impedance. If it's minimum admittance, the last element would be series. So the point is, in a minimum impedance network, if you know the resistance, you also know the reactance. So that's good news, because if you then approximate the resistance and you fit the function to this as smooth polynomial, a rational function, which is positive real, then you also know the reactance, you also know the impedance, which means you know the network. So this is a very good technique in the sense of it converges very well. So it is meant for single matching, which means only one side is complex, but you can fairly easily define these segments on a conjugate match basis, and then you have to fit a function to get the polynomial, which is the approximation step. So you will lose some accuracy there. Then you extract the circuit. So everything is fine if it's low pass or high pass, but if it's band pass, you may need transformers in that network. So when you extract the network, you may find you need transformers. So while it's good, it's not very usable for real problems. So it has its advantages, but ultimately it's not going to do it for you. Now this was extended for double matching. Now the double matching things are good, but the convergence is not the same. So it's like we've heard before about the harmonic balance. It's very dependent on how you initialize. So what you can do, you take this line segment thing and the results from that you use to initialize this double match problem, and that works pretty well. So you can get good results by doing that. But note, we didn't talk a word of harmonic control. We're talking matching. So we're talking fundamental frequencies. So again, nice to explore, but ultimately it's not going to do it for you. So next thing up, transformation queue approach. Now this is sort of admitting defeat. So I can't get it by optimization because I don't know how to initialize. So I do a search. Now, what can I search on? If I search on components, it will take forever. I don't know how to find the search. Now, fortunately, there's a thing called the transformation queue. Now, what is that? This is this. So basically, if I look at what is happening in a matching network, there's a resistance there, there's an omega L there, and that has reactance. Now, that considered as an impedance, R plus J omega L, if I consider that as an admittance, it is a resistance in parallel with the inductor. The Q is the same. So basically, this ratio to that ratio is a Q. It can have a sign. If there's this capacitor, it will be negative sign. So if I look at the parallel combination, that RL has changed. It's not RL anymore. And this is how it works. So that RL starts as RL, but then it turns to Rin 2, sub 2. And the step size is 1 plus Q squared. So whatever this Q was, I can control the step size. And then I add this element, so I change the Q, and I take this parallel combination, and I look at the series equivalent, and then I have a new series resistance, and this will be the new resistance. And then the same procedure goes on until I get to the end. So basically, series elements take you higher, shunt elements take you lower, and this so it goes with this process until it gets to the end. So effectively, if a Q is very high, the bandwidth will be narrow. And so it's just like a circuit queue. So these queues, the circuit queue, if these numbers were big, so it was 10. So then the circuit queue would be 5, it would be half. So they cannot in principle be big. So this is a nice thing to search on. I can get it done. Now, good news is, apart from that, if I also control the gain, so these Qs are calculated at a fixed frequency. So I select the frequency, that's maybe the center frequency or whatever. I calculate the Qs there, I search on them, and at that frequency, I also control the gain. So if I have a good match, the gain will be more than. So I assume the gain will be more than half a dB or whatever. And I then have a circle of the size. But if I have this circle, and I know the source impedance, the circle is known, then the resistance cannot be outside the circle, and the reactance cannot be outside the circle. So it limits the Qs. So the last two Qs, so Q3 and Q4, they're not independent, they link to the gain. So this makes it quicker too. So apart from the fact that the Qs are limited in range, I then also have the gain to help me because the Qs cannot go too wild. The gain put a further constraint on them. So one can do a search, a realistic search on the Qs for up to 6 elements unconstrained, fairly efficiently. This is an example of using that Q technique. The same problems before, the 100 ohm to the 50 ohm. This time you see if I do a lump design, this can do, the stupid doesn't have to be lumped. But lumped usually gives good results. So you can see that's pretty good. It's over 2 to 4 gig, and it got to pretty small dots. So the technique doesn't have any problem finding the answers. Now that is fundamental problem. What about the harmonics? So for harmonics, we need traps. Now, what is a trap? A trap basically says I have a second harmonic, I would like to kill it off, so I need a transmission null. So ideally, I need nulls for the harmonics, but I need more. Because if I just have an external short, intrinsically, it will not be a short or an open. Maybe I want to open, maybe I want a short, maybe I want a specific impedance. So I need a line section. So when I have this trap here, the impedance is defined. Now it could be a short trap, or it could be an open trap. And that doesn't matter, so it's my choice. But as a rule, it would be shorter because that's easier to implement in microstrip. But I could make a parallel trap with a lump component with parasitics. So basically, there could be a line section, and this line could transform this to whatever I need to keep a transistor happy. Now, if this line is short, I can add the trap before I design the matching network. Now, that unfortunately doesn't happen often. So example, these are examples of traps for the 10-watt Cree device. So this is different frequencies. The passband is quite wide here. I think this was for 1 gig to 3.8 gig or something like that. So there's a 5 point, let me see where our frequencies are. 4.4 gig frequency, 6 gig frequency, 7.8 gig frequency for the second harmonic. And the third harmonic is 8.1, 9, and 11.7. Now, important point about the trap, it's fine. It trapped the harmonic, and I have some main line. This is what this is, main line. This main line will transform it to what I want intrinsically. But what does it do to the fundamentals? So if I have a trap, it's doing the right thing for the harmonic, but what is it doing at the fundamental frequency? Now this measures that in terms of Qs. So there was some original Q. It was listed here in the corner, but I took the corner off here. So that Q was degraded maybe from say 2 to, let me just see, this is worst case fundamental Qs. So basically the Qs gets degraded, and this is less degraded, and this one here, well, it didn't have, it's a different one. So this one's the least degraded. So basically this trap will not mess up the Qs very much, but this Q is on the load side. Let's see, this one is on the source side. So point is, if you look at this table, it will tell you how much the fundamental is messed up. Here we have reactance values. So it's the fundamental reactance is sort of in the order of 30 ohms. So this thing will at the highest frequency give me an extra 53 ohms loading, 99 ohms, 250 ohms. So basically it will load me fairly significantly. So 30 ohms is not far away from 50 ohms. So the loading is not insignificant at the fundamentals. This one which I selected, the loading is 80 ohms. That's fairly much bigger than 30 ohms. 140 ohms and 370 ohms. So this is a useful table. I can at a glance say, I want to cover this frequency range. For that frequency range, I can have traps here. With these traps, I need these main lines to get what I intrinsically need for the mode I target. But what does it do to the fundamentals? And basically with this table, you can answer that. So this purpose of this table is to decide, can I add traps before the time? Before I design this matching network, are there some traps that are useful? And basically, only one I would pick here is that one. So it's a third harmonic trap that will do something for you at the very high frequencies, but it's not going to do much about the other frequencies. So that would be trapping. Now, a better way for traps is to add the trap in the matching network. So you don't decide beforehand where the trap should be. You let the matching network decide where the trap should be. Now, if you think of that matching network before, the Qs, so this, you control the Q, which means you control the reactance. You decide what the reactance should be, and you do a search. So the reactance can be small, can be negative, can be positive. So it has a range. And this has a range, and this has a range, and this has a range. But now we add one more. This is for the fundamental. Now, if we also control the harmonic trap, so this doing two things now. It's doing the fundamental and the harmonic trap. Then we have control over the harmonics too. So that is what this is doing. So if we look at this, so one simple way is I have a shorted stub. I make the length, this is the open stub. I make the length for presenting a short at the harmonic frequency. Then I make the characteristic impedance to give me the right loading. Now that is fine, except that there's a junction here. And if this is a nasty impedance, it's going to give me a lot of discontinuities. So I am limited in what I can do here because I might create more problems than I would like to have. Similarly here for shorted stubs. So basically the length will set a null. I can change the width to get the impedance I want. Now this is better. I can use a fixed line which has well-behaved junction, and then I can terminate it in an open stub. So basically this is maybe a 50 ohm line, and this is a 25 ohm line. Now this has also a resonance frequency somewhere, so I can make it resonate at the frequency I want, and I have more control over what the impedance will be. So this is a better plan. So this is workable. And then for the shortest stub, this is more complicated, but it's still a good plan. So I use a reasonable width for, usually you want the highest width you can, the thinnest line you can for the shortest stubs, because I mess up the low frequencies. So I want a thin line here. And then I have the short, but I don't have the right impedance. So I load it with one of these things. Then the combination will have the right shunt loading, and off I go again. So you can see here, if you follow this procedure, I basically have control over the fundamentals and I have control over the harmonics. So that is the purpose. So that is a quick covering about how going about using the transformation queue approach. The next phase is discontinuities, what to do about them. So I have these junctions, and if I ignore them, I will have a network which is okay, but it's going to deviate, especially at the harmonics. And that is what I want to control. So one has to make a plan. Now, there are many plans to be made. You can have a very accurate models, which is difficult, especially if you want to go to the harmonics, because it's very wide bandwidth. So that's not so easy. You can rely totally on EM simulator. So I have what I have, and the EM simulator must fix it. So I have a target from this, but the EM simulator must optimize to get it right. Or I can use what ADW, replace all junctions with S-parameter based simulation for that junction. So I call it an S-parameter based junction. So basically, if you look at this matching network, there's a junction there. So that junction becomes S-parameter based, comes from an EM simulator. So I take this junction, put it in the EM simulator, and from that put in the junctions here. So it's not like just a simple export. This junction gets export characterization, S-parameter characterization. Similar for all the others, and you can see what happens in the end if you compare. This is a comparison of ADW performance and EM performance. They're spot on if you put in these junctions. Now, there's one extra point to note. You should separate the junctions far enough. So if they're too much on top of each other, they're going to couple with each other, and it's going to mix you up a little bit. So as a rule, if you look at the separation and you model these things with S parameters, you're going to have pretty good accuracy. So it's not going to be a big discrepancy. And this ADW is set up to make this process very efficient. So if you have a circuit like this, it can auto, when you use export, it can auto create all the junctions in circuit files. And then those they set up already for EM simulation, but it's an ADW circuit. Then you can export that to say Sonnet or Axiom or whatever. Do the simulation, import it back, and the naming conventions follow the so you can very quickly import it back. So it doesn't take long. So maybe for this thing, in half an hour or so, you can have all the junctions back in here. So it's not a serious process. And then it's very accurate from there on. So nothing to worry about. So that is basically the approach followed here with EM stories. Next thing up, how about nonlinear CDS? We've seen nonlinearities can measure up. Now, obviously, there's also CGS, but we're not worried about it at the moment. This is load line control. So this is CDS. Now, there are papers that show that it's not necessarily bad to have nonlinear CDS. It can actually help you. Now, it's not always true. So how does the ADW deal with that? Well, it can actually calculate that. So here's an example of load line assuming linear CDS. So then load lines would look like this. Now, if it's non-linear, they look like that. That's interesting. So that actually helped. So they're hugging the knee much better. So in principle, you design the circuit linearly, then you check out what does non-linear CDS do to the circuit, and if necessary, you adjust it. Sometimes you're lucky and it's just better, so it's nothing to do. And if it's worse, you can optimize it to fix that, and then export it for full harmonic balance control. And this is an example of what you would do in the ADW. So you have targets. So this is fundamental. These would be targets for second harmonic. These would be targets for third harmonic. And then I designed the matching network, and it's doing what it should. So I just made the frequency range this bit, and then low frequency range for where the second harmonic starts, and low frequency range for where the third starts. So it makes lines instead of a curve, so they can see where the frequencies are. So that's why I did it like that. So basically, fundamentals inside the circle, so it's doing it, and second harmonic inside the markers where it should be, it's fine, and the third harmonic inside the markers. So this is what you typically want. You have these targets, Now the software automatically made the segments, but I show the markers because they're more significant than the segments. So that is an example then of taking harmonics into control. This is more complicated. This is a 10-watt Cree device, a matching network for that. You can see there are harmonic traps here, but they're lumped. So that inductor resonates with that capacitor and the lines to create a short at that point. So this is a short at harmonic. And this is similar here, short at harmonic. This might be short or not, so it depends on whether it's possible or not. And then effectively, that's what the passband is looking like. It's running around there in the middle. And then it's going like so. Now you can see this is not far from class B. Now this is a terrible bandwidth. This is 1 gig to 3.9 gig, very wide. Effectively, in some parts, you cannot control the harmonics because the second harmonic is also the fundamental and the third harmonic is also the fundamental. So you simply cannot control it there. But the software understands that, so you can set it up for that. So where it's controllable, you can see that it's best to make a class B. So there's always the story about we need all these continuous modes because we cannot do wideband specific class. Well, this is a wideband class B, sort of. You typically, yeah, I'll show you a bit later another one, but effectively, this was done by using traps. This is a more complete example of a PA. This is just theoretical, it wasn't built. But you can see there's the trapping mechanism. There's more trap. So it looks like that. Effectively, the load line looks like that. Again, a class B, which I wanted. The dynamic load lines look good. The gain is not very flat. The gain is the red one. The efficiency is this one. But this is quite good performance if you compare to what is achieved elsewhere. And this summarizes the whole thing in the passband. So it's conditionally stable. You can see it's not above 1, but it is pretty well stable. So you can have quite a lot of deviation in the load before it gets unstable. Gain is the power is fairly flat. Efficiency is above 55. So it gives you an idea. I added this one. That's an interesting paper. If you look at the references, this was a paper by Yang. I put this on purpose here because this is a very good paper. So if you want to understand how to design something properly, this is a good thing to read. So I like that paper. So I took their matching network and I put it in